In this video, we'll take a little bit of time to introduce what's known as a slope field. If you're in an AP course, the College Board exclusively uses the term slope fields. The textbook that we're using, other textbooks are going to possibly call these direction fields. So slope fields are things that help us approximate solutions to differential equations. They don't give us solutions to differential equations. So one of the things I want you to be able to see based on the outcome of this video is the relationship between the solution to a differential equation and the slope field that is built from it. So by the end of this little sequence of videos, we've got to be able to build a slope field successfully. We won't be doing that within this video. We've got to be able to match up a slope field with the differential equation that it would have been built with. That's a pretty typical sort of situation to be faced with on the AP exam. And then we also want to be able to approximate what a solution curve to a differential equation is going to look like by drawing it into a slope field. And that is actually something that we'll do by the end of this video. So this is what a slope field looks like. It looks kind of crazy. Computer software was definitely used to generate this one. We're actually going to use Desmos to build a slope field before the end of this video. But a slope field is going to be a sequence of line segments whose slopes indicate the slope of the tangent line to the solution curve that fits into it at the given ordered pair. So this thing is difficult to define verbally, but think about how I'm about to use this. So I'm going to show you how a solution curve to a differential equation fits into this slope field. The differential equation would have been used to generate this. We're going to do that in an upcoming video. But if we have this and we know, say, that our solution has to go through the ordered pair 0, 1. Actually, let's go 1, 0. If I'm trying to draw an approximate solution into this, let me get a little thicker pen here. I need to recognize that this point has to be on my solution curve, and I just have to use the slopes that are in front of me as basically a roadmap to kind of guide my curve. So I'm having slopes that get bigger and bigger as I work my way up into the first quadrant. Now as I come down across the x-axis here, way down into the fourth quadrant, you see that these slopes are really level down in this stretch of the graph. And so as I allow my graph to sneak down into that quadrant and approach the y-axis, that wasn't a very good attempt at this, approach the y-axis, I eventually have to have a horizontal tangent line at the y-axis look up and down the y-axis. You see horizontal line segments. So whatever my graph does as it passes through the y-axis, it has to have a horizontal slope for the tangent line. And then as I work my way down into this quadrant, I see that the slopes are getting bigger and bigger. It's a little difficult to do this with a mouse, so it's much easier to do this if you are actually drawing it in on a piece of paper. But you'll see that the slopes near where my graph is within the coordinate plane, they are pretty much spot on for the slope of my tangent line. It is definitely a better situation to have the solution to a differential equation like we would get when we use the method of separation of variables and do the antiderivative of each side, as we talked about in the prior lesson. But if you can't separate the variables, if you can't solve the differential equation with a method that you know, you'd have to wait till your differential equations course in order to be able to solve that differential equation. So having an approximate solution to it, even if we don't know the equation, the function that graphs this curve, we still have the ability to approximate y values. If I wanted to say what the y value was at 2 for the solution, I can go up here and I can say it's maybe going to be like 2.5 or 3, just based on the fact that this graph is going to extend up a little bit beyond the y value of 2 if I extend it over to the x value of 2. So this is better than not being able to do anything until you take that differential equations course. This is a problem that we actually solved in our last lesson, so I'm not really going to go through the steps to solve this again, but what I want to make sure you can recognize is the relationship between a differential equation and its solution along with its slope field. So when we solved this by separation of variables, what we did is separate the variables, integrated both sides, solve for y, got this solution. Now this is a general solution because we don't know what that value of a is. So the directions here actually said to sketch several members of the family of solutions. I actually use Desmos to do that. So if you look at this general solution again, if we're sketching several members of the family of solutions, we're just going to be popping several different values in place of the A value and see what we get. And here's what I got on Desmos. So you'll see I did this 6 times. I used values of 0.5, 1, and 2 in place of A. And then I used values of negative 0.5, negative 1, and negative 2. And you can see what these graphs look like. The ones that all have the positive values for A all definitely resemble each other. Now they're not the exact same graph, obviously, because they're not the exact same equation over here. But all of these graphs, all of these equations do have the original differential equation as a form of their derivative. So they all have the same derivative, so the graphs all should have similar properties to each other in certain spots. So the next thing I want to do, I'm going to click into my Desmos window real fast. So Desmos has the capability of generating a slope field for you. It's not within the normal graphing calculator portion of the website. So if you just Google Desmos slope field, it'll be the first thing that pops up. Click the link and it'll give you the, whoops, didn't want that. Let me see, I hit the wrong thing there. Let's try that one. It'll say this by default. So let g of x equal dy dx, or excuse me, g of xy equal dy dx, and then it gives you the opportunity to type in what you have for g of xy. And if I go back and show you what that differential equation was that we were dealing with a few minutes ago, it was dy dx equals 2x times y minus 1. So that's exactly what I typed into Desmos here. Now I'm already kind of zoomed in on this slope field. If I zoom out, and I can change different settings here to show more or less of the slope field. What it does is it gives you this little point that you can move around. So I'm going to zoom back in. The segments that you see here, the slope of them is the value of this derivative at the ordered pair that it occurs at. To just kind of confirm that, check out this ordered pair 1, 2. At the ordered pair 1, 2, we see what, kind of like a medium positive slope right there within the slope field. What happens if you take the x value of 1 and the y value of 2 and plug it into this derivative? Well, you're going to get 2 times 1 times 2 minus 1. So what, 2 times 1 times 1 if you simplify that, and that'll give you 2. So this line segment has a slope of 2. Our solution curve, if it goes through this ordered pair 1, 2, it has to have a slope of 2 at that ordered pair. So if I wanted to kind of visualize what the solution curve is going to look like, what Desmos does with this little draggable point is if you move it around, it'll let you kind of see what the slope is going to be anywhere on your curve when you move this point to a new spot in the coordinate plane. So when I put it right on top of that ordered pair we were just discussing, we see the slope of positive 2, and then I can bring it up to this point here at 0, 3, and I see, if I get it close enough, I see that horizontal segment show up. The other thing I want to show you here is I have this graph ready to activate. I'm not going to do it just yet. I'm going to click back to the file that we were working through. And this is going to be this graph that you see in orange here. So you can kind of visualize what the graph's going to look like once it shows up. Before I activate it on Desmos, what should happen is we should see that graph go through the point. Let's see, what was that ordered pair again if we go back to it? What, just slightly below 2, maybe like 1.5, 2, and I guess we can confirm that, right? If I'm thinking about where this graph is on the y-axis, I know that x is 0. If I put 0 here, I get 0.5 times e to the 0. Well, that's 0.5 times 1 plus 1. Yeah, that's 1.5. So when I activate this graph in Desmos, what has to happen is I have to have a graph that goes through the ordered pair right here, right, 0, 1.5. And as I work outward both directions, I have to use the slopes that I'm seeing kind of as a guide for my graph, just like we did a couple minutes ago whenever we drew a solution into a slope field. So if I go ahead and activate this real fast, you're going to see that graph, if we move back and forth across it, we have that 0 slope at the ordered pair that we knew we were going to hit the y-axis at. And as we move across the graph into the first quadrant, we see that our slope of the tangent line is indicated by the slope of this segment that's moving across the graph here. So the derivative, the value of the derivative at the ordered pair that you're sitting at, indicates the slope of the tangent line there. If you have the segments drawn like we've been talking about within this video, you have that roadmap to kind of guide your graph. So the differential equation builds the slope fields by indicating the slope of the solution that fits into it at that ordered pair. The solution to the differential equation is going to have the slope indicated by the segments from the slope field that sit near where the curve is passing through. So what we're talking about right now is not really an authentic situation of where you would use a slope field. It is much, much better to be able to do what we did here. Solve the differential equation with a method, get the function that satisfies the differential equation. If you can't do what we did here, then having the slope field is better than not having the ability to estimate what that solution curve is going to be at all. In the upcoming video, we'll actually build one of these from scratch. That's something you're going to need to know how to do in order to have success with matching these up with the differential equations and different situations you're going to encounter on the AP exam. And then eventually we'll actually do a little bit of that matching in a video that follows that one.